Hi friends, let's have a look at problem 874, Walking Robot Simulation. This is today's daily challenge problem. So we are going to share a solution which is linear in time. So here we have a robot on an infinite xy plane starts at the origin, facing north. The robot can receive a sequence of these three possible types of commands. So one is -2. It means that turn left 90 degrees. One is -1, means turn right 90 degrees. And another one is k is an integer, positive one, between 1 and 9 inclusive. It means move forward k units along the direction. So here the constraints are the following. First, some of the grid squares are obstacles, and the ith obstacles is at the grid point I. If the robot runs into an obstacle, then it will instead stay in its current location and move on to the next command. So we want to find the maximum Euclidean distance squared. So here we have several examples. So if you look at example 1, right? So the robot is starting position, and this is the point it passes. So in other words, its trace passes these points. So we want to find the furthest point to the origin. So here 3 and 4 is the furthest. So if you compute the Euclidean distance square, it will be 25. So this is our return, right? So if you look at example 2, so notice that here is a block situation by the obstacle. So these are the points it passes, like 1, 4, right? And then it reaches 1, 8. So overall, the output is 65. So for the third example, so first it moves upwards 6 units, so you arrive at 0, 6, and then it changes direction to the left, and to the right, and to the right, and then turn right, then downwards, right, and then it moves downwards 6 units to 0, and the points it passes are 0, 0, 0, 6, and 0, 0. Then the longest Euclidean distance square will be 0 square plus 6 square, that is 36. With that digest, let's also look at the constraints. First, this is the length of this command. So basically it gives us the problem size, right? And the commands are of the form either -2 or -1. It means these two instructions mean change direction, and also a integer in the range 1 and 9. So this is the bounded range, right? So this is the length, right? Obstacle length. And also this is the bound for xi and yi. So the last one is a consistency assumption. So with that said, let's look at the problem. So first we are going to point out the main point, and then we are going to do the coding. So the main point is in the statement. So if the robot runs into an obstacle, then it will instead stay in its current location and move to the next command. So what does this statement imply? So here we can digest it using an example. So assume that we are at the origin, right? P equals 0, 0. And then the direction is in the positive y direction. So if we want to move 4 units along y, in other words, the command, let's say, is 4, right? If there were no obstacles, then the destination position would be this one, right? So move forward, move upwards 4 units, you get 0 and 4. Then the trace would be the following, right? You move from 0, 0, then to 0, 1, to 0, 2, to 0, 3, and to 0, 4. In other words, it jumps from 0, 0 to this 0, 4. The reason why we consider trace is due to the obstacles. So here, if there were obstacles, for example, we have 2 obstacles at 0, 2 and 0, 3, then the above trace would stop at 0, 1, right? Because if you continue moving forward towards 0, 2, and 0, 2 is an obstacle, right? And then by the assumption or the statement of the problem, then the robot will stay at position 0, 1 and wait for the next command. So once we realize or digest this point, then doing the coding will be very straightforward. So here also I want to make a comment. So the positive commands will be in this range, 1 to 9, right? And then we could see that we can use a for loop or while loop to check the to locate the position in the above example, right? So here, for example, this case. So another thing is that, so here we have a list of obstacles. So we can transform this list to be a set. This is for convenience of membership check, right? So with that said, let's first, we need to deal with one thing and deal with change of direction, right? So originally we have a direction, then we want to change direction. So if you know some mathematics, so we know that if we want to rotate in a counterclockwise theta degree, then the rotation matrix will be something like this: cosine theta, cosine, let's say cosine A, negative sine A, and sine A, cosine A, right? So where A is 90 degree or pi over 2. So this is you turn, let's say turn left, right? If you turn right, you are going to get, so this is for left. For right, A is negative 90 degree for right, right? So we can use matrix multiplication to trace the direction. So let me first write this hyperfunction, right? So we can define a matrix multiplication, right? So we accept a matrix and then a vector. So here V is direction, right? So we can, in this problem, M is a 2 by 2 matrix. And V is a length 2 list, right? Then basically we want to do matrix multiplication. This is very straightforward. So basically we want to use the matrix, the first row, right? Multiply by the vector, so V naught, right? And then plus the first row, the second element, times the second element of the vector. And then we copy this and we do it for the second row. It's going to be M1, let's see, M1 0 and M1 1, right? So, and this is, let's use a list format, right? So this will be our matrix multiplication. With this, we can do the other parts. So originally our position is the origin 0, 0, right? Oh, another thing. So we want to convert the obstacles list to be a set. So this is for membership check. So this is actually very straightforward. So we can do obstacles. So we are going to make it a set. And first, because the elements in this obstacles are also list. List is mutable, right? So we need to transform it to say tuple. So tuple atom for atom in obstacle. Let me copy this part. Yeah, this will do the so these two parts finish the preparations. Now let's look at the logic of the problem, right? So this original we have a direction that is upwards along the y direction, right? Now also let's initialize a result variable. So this is what we want to return. So notice that this is the point, the distance of point, let's say, to the origin, and then squared, right? This is what we want to return. So now I think we can do a for loop. So for command in commands, right? So if command is say -2, it means turn left 90 degree, right? So here we can prepare two matrices, right? the matrices. Let's see. So actually, this matrices should be class matrices in general. So let me do this. M left. So it will be, so when A is 90 degree, so this will be 0, -1, and 1, 0, right? Then M right, it will be 0, +1, and -1, and 0, right? So then if the command is -2, so we want to change to the left, right? So the way will be updated like this. So we have a matrix multiplication, and then the matrix will be M left, then times this way, right? Otherwise, so if the command is -1, so then V is updated like this, M right, so V, right? Another case is that we want to move, right? So let's first get the direction. So dx and dy is V, right? So we just unpack this, and then we get the line. So because we want to, along this direction, move this command units, right? So the line will be something starting from the position and then move towards along with this number of steps command, right? So let me write like this. So position 0 plus k times dx. So actually for this problem, one of the dx or dy would be 0. In other words, so the one is 1 or -1, the other is 0, right? Because we only have up, down, left, and right. So position 1, so plus k times dy for k in range. So I'm going to write like this, command plus 1. So if you have k equals 0, and then this is the position itself. If you have k equals command, this will be our destination point if there were no obstacles. So notice here, I'm writing like tuple. The reason is that I want to do a membership check against the obstacle set, right? So here we can use a while loop to mimic the movement towards the destination point. But in between, if we met obstacles, we are going to stop. So basically, while I is less than the length of this line, and then we can get the point. So the point will be the line at the current position, right? So notice that this P is a tuple, right? So let's see. If P in obstacle, so in this case we need to stop, right? So it's the break. Otherwise we just increment I by 1. So afterwards, so we will have two scenarios. Either I equals the length of line. In other words, we didn't meet any obstacles. Then we are going to set our destination to be the last point in the line. And otherwise, we are going to set the point to be the point at index I-1 in this line, right? So what we want to do is the position will be the line at index I-1, right? So this actually will be okay, though here the position, if we use this, this is actually a tuple, but here it's a position. But this will do the job, so I will not do the type conversion, right? So always what we want to do is passing each command. So we're going to do result is max. So the position at 0, so square root, square, not square root. Position at 1, then square. Then we compare against the previous state. Then afterwards, we just need to, let's see, return the result. So this is the one way to do the problem. So before we make any further comments, let's first do a test. Yeah, it passes one example. Now let's look at this example. Yeah, it passes the second one. Now let me also check the last one. This should be 36. Yeah, it passes all the examples here. Now let's look at the generic case. Yeah, it passes all the cases. So here, let me make some comment to end this video. First, we made some preparations. For example, the two matrix got involved and the matrix multiplication. And then we transform or convert the obstacles list to be a set, right? This is for convenience of membership check. Then we initialize the position and the direction, and then we initialize a result, and the final state of this variable is to be returned. And then we do a for loop to check the commands. So if the command is -2 or -1, so we are going to change the directions, right? And then otherwise, so we first get the direction, and then we produce a radiated line, right? And then this line is starting from the position, current state of the position, and then along a trace move to the destination point, that is position 0 plus command times dx, position 1 times command times dy. And in between, if we meet some obstacle, we need to stop one step ahead. Otherwise, we can move towards the destination point. So this part from here to here is to set the position. So you can think of this example here, right? You start from 0, 0, and you have a direction, and here you have obstacle. Then you should stop at the point 0, 1. So this is exactly there. And then for each iteration, right? So here you can look at the alignment. So or indentation. So we do a comparison of the current Euclidean distance square state and the position, the distance square of the position to the origin. Then we do the return. So with that said, I guess that's about it for this problem. So in reality, it might be good. So for example, you use mLeft and mRight as class variable, and then write this function as a class method. Then you do this part. That might be better. So from a architecture point of view, but for solving this problem, this code will be sufficient. So with that said, I guess that's it for the current video.